Business Calculus, Topic 5.5, Number 13. The base of a 50-foot ladder is being pulled away from a wall at a rate of 10 feet per second. We want to know how fast is the top of the ladder sliding down the wall at the instant when the base of the ladder is 30 feet from the ground. Okay, the base of a 50-foot ladder is being pulled away from a wall. Let's draw a wall, and also we need a ground. So there's the wall, and there's the ground. And we also need a 50-foot ladder. So here's our 50-foot ladder leaning on the wall. Okay, 50 feet. Okay. Now what's happening is that it's being pulled away from the wall at a rate of 10 feet per second. So this part right here is moving, and that's moving at a rate of 10 feet every second. Okay, so it's moving that way. 10. So every second, it's gone another foot. All right. Question is, how fast is the top of the ladder sliding down the wall? That's this part right here. What kind of rate is going on there sliding down? Well, if this is marching out at feet per second, this is also going to march down at feet per second as well. Okay, let's see. And we want to know what is the speed as it slides down at the time the ladder is 30 feet from the ground. So when this gets down to about 30 feet, let's say 30 feet is about right here. What kind of speed will this thing have when it gets to this spot right here? So it must mean that the different speeds all as it slides. It might be sliding slow here and faster as it gets to here. And here at this spot, we want to know the exact instant speed there. Okay, let's look at what we have. Feet per second, that's a measurement of the change in feet. Well, change in feet going this way. Well, we got to have a letter to measure the distance going this way, which will be in feet. And this looks like an x-axis, so I'm going to use the letter x. So it's the change in x, the change in the x's, per the change in the time, which is seconds. So let's put change in time. So to represent the speed here, I'm going to use a dx over dt. This is the change across the x's versus the change of time. Also need something to measure this, so let's go here. Now I need the change in the feet going up and down versus the change in time. Well, going up and down, the change in feet, I want to call the feet going up and down, let's say the letter y. It's a good rule because we usually use y for vertical. So the change in the feet y per the change in the time. Now this we don't know, but this one we do know. Lastly, I need a relationship between the feet here, the feet there. So the feet here are all y's, the feet here are all x's. Well, this is a wall, so that's a 90-degree angle. So we can use Pythagorean's theorem to represent feet here and feet there. So it'll be x squared, the feet here squared, plus the feet here squared. That's going to equal the ladder itself squared. So that's 50 squared. So this will be x squared plus y squared equals 2,500. Now we need to take a derivative of this, but how do we decide what kind of derivative we're going to take? Well, take a look at the denominators. These are all dt's. The denominators indicate what kind of derivative we want to take of this. So we're going to take a derivative of all of this with respect to a t. Now you notice there are no t's in this at all. If there was a t in here, we can take a simple derivative of it because this indicates what the variable is. Well, since these are not t's, that means that anything else other than a variable would be a function. So x is a function, y is being treated as a function. So when we take a derivative of these things as functions, we need chain rule. Here we go. So the derivative of x squared with respect to t will be 2x. Okay, that's a derivative. But then times the chain rule, which will be dx over dt, the change in x per change in time. Again, because x is being treated as a function, this comes out according to the chain rule. Now, plus the derivative of y squared, which is 2y. But again, y is being treated as a function because t is being treated as a variable. So this will be times the chain rule, dy over dt. Now the derivative of a constant is going to be 0. Okay, so again, a couple chain rules here. Alright, now, what we're looking for. We're looking for the change in the y's per change in t. So we're looking for what this number is, or that rate right there, whatever number that is. And we do have the change in x per change in time to be 10, so we know what this is. And the x distance, we don't know what that is. The y distance, let's see, 30 feet. Yeah, the y distance is right here. So we know y is 30. So we have this guy, this guy, this guy. I'm sorry, we're looking for this one. But we have this, and we need to know what that is. So, that distance. Well, we know, according to the Pythagorean theorem, if this is 30 here, 30 feet, and this is 50 feet, and this is a right triangle, the feet that's over here, the x feet there, can be found by 30 squared plus x squared equals 50 squared. This will be 900 plus x squared equals 2500. Subtract 900 from both sides and we get x squared equals 1600. And then the square root of both sides gives us x equals 40. Okay, so when this is 30 feet, this side will be 40 feet. So that's my other x. So let's go ahead and put all those values in. So 2, the x value, which is 40, the dx over dt, which is 10, 2, and the y is how many feet, which is 30. And we're looking for the change in y per change in time. Okay, when I multiply all this together, we're going to get 800. Multiplying this, we get 60 dy dt equals 0. Alright, subtract 800 from both sides, and we get 60 dy over dt equals negative 800. Divide both sides by 60. And I end up with dy over dt, the change in y per change in time. The zeros will cancel, and I'll have 80 over 6. Half of that will be negative 40 over 3. And 3 goes into 4 one time, leaving about 10 left, and that'll go in there three more times. So about negative 13 with the repeating 3. So just about 13 feet per second it'll be moving when it gets to this spot right here, when this part moves to that spot.